Okay, today we're going to be looking at 7.3 milliamps being drawn through a high voltage circuit consisting of a neon bulb. Oh, I'm sorry, yes, a neon bulb, smaller 3 to 4 inch neon bulb discharge leading to plates between a magnet, and the yellow wire is going to the top plate of the magnet with the poles across the electrodes and then back through to the source. We're looking at a draw then of 7.3 milliamps from the system. Now these wires here are yellow and green going through the amperage meter in conjunction where we're measuring it on the circuit of this series magnet bulb discharge path. We also have yellow and green input wires to the entire process, which are here. Now what we're going to do is take these wires off, and we're going to measure the current limit to availability of current from the system itself. Sometimes it takes a region to stabilize. We're having a problem here. Well, we'll be taking them wires off. Show how much current the system can supply without the load. Didn't plan on this prerogative. Well, I seem to be having a problem here. I'm making a mistake on where I'm supposed to be measuring from, but we're trying to see again. I don't know how I make these mistakes. What the load itself can deliver, only to show that it's only slightly higher than what we're drawn, and being some 7.6 milliamps. Now, overcoming that problem, let's put it back into the original orientation. Took the amperage meter out of the circuit. Hook up the input circuits to the point where they're supposed to be, which at times does become confusing. This is the yellow wire. It goes into one potential. We like to put that potential behind things. Yellow is the higher one. It goes through that coil. Okay, we're going to energize first the helium bulb, of course. Oh dear. And down, of course, latch bulb. Now we have never yet completed this connection, which is to go from there to there. But as we can see, there is no bulb illumination, and we only have one wire left to complete that connection between the magnet and then the and as we can see then, we have a need to look at the closest scopings now. The camera assistant can oblige to focus in on each signal. Here we are looking at a signal of 50 microseconds at 2 volts per division. However, our signal isn't being cohered. With this Textronic scope, we have a level indicator that can show the degree of coherence of that signal being received. I like to receive the signals in this manner, showing somewhat a plethora of signals, but many people are in the regard that the signal should be focused to be the cleanest wave. So here we have the cleanest wave coming from that. And that signal then at 50 microseconds per division is obtained from the 1.2 mile twice 2.4 miles of coil being obtained by the helium bulb discharge from the potential. Now again, once again, we will open the potential, and to see the difference of signal, we obtain more signal without the energization of the gas. Well, we're not going to go with that very well, but we can see the big difference of signal, and the signal is not primarily dependent upon the gas illumination itself. Now, every time we open and close this circuit with this instrument here, it seems that we need of connecting it. Excuse me. So we're looking right here. I don't know if that meter is very important, but it should be for the end of this thing, since now we want to measure the current of this discharge, whereby we just do the traditional thing and break the circuit. I always worry about damaging my meters working with the high open circuit voltages. Well, see, those you're drawing arcs to your meter lead. Ain't a nice thing to do for a nice piece of equipment. Now, of course, now it's going into a fluctuating state, which usually stabilizes out. Who's to say what that's for? You can barely top it. It will help. Okay, well, for the end of it then, we've seen that we've got 7 milliamps going through here, and normally it will immediately stabilize on turn on. I'm going to go over there and turn it on and off, and we'll look at our power input and we'll be done. Well, apparently for some peculiar reason, now it wants to blink again. This could be due to a variety of factors. I don't know. Well, you got to repeat something and it won't work when you want to tell it to. There's a number of things I suppose that could go wrong. Position of leads and metering. But we should try to get to the end of this BS. Go look at our power source then. I don't know why it's doing that. This isn't very conclusive, but I don't know. Let's just get the rest of this done with. We're tracing it back down to show where the power source is. These are the binary resonant coils. And then to obtain about all this, we got 40 milliamps on the back coil and about 30 milliamps on the front coil. And that's about it.